Okay, hello guys. Thanks for joining these AI sessions. So my name is Yvon Ranou. I'm in charge of technical marketing for Germany and some other key customers. I'm located in Munich and I'm covering essentially Bavaria and some other customers. Okay, so let's start on this AI artificial intelligence. So I will start with a small marketing introductions. After that, you will go with Guillaume a little bit more in depth in terms of technical, what is behind this big word AI, and we'll spend 60 minutes together to practice on the current use case with the AI Cube tools. So, artificial intelligence, we launch a new tools. The name is STM32Cube.AI. So this is an extension of your cube you know very well. And we launch these tools at Embedded World this year. So it's now fully available and we are supporting customers with AI application with these tools. So this a neural network, to build an application of a neural network, you have to go different steps. The first one is data capture. And for this, you need some hardware with some sensor. So this is a brick, first brick you need. After that, when you have a big collection of data, for sure you need to make some cleaning and you need to build your neural network. So this is not a part where we are directly involved because this is not our business, and there are a lot of parties, third parties, offering tools to do this, like Keras, like Lasagne, and some other guys. So you have to use an existing tools on the market to build your neural network on your workstations. After that, you have to train your neural network for your applications. And again, this work has to be done on the workstations. Until you have your model and your neural network working as you expect, you have to convert it to the embedded world. And this is where ST is bringing innovations with these new tools, this Cube AI converter. So what is it? It's a converter from a neural network working on the workstations with a lot of power, a lot of resources, optimize it for the STM32. Okay, and this is what we will do together. We'll practice to see the added value of these tools. And when you have your neural network working on the STM32, you can start to do some process on analyzing for your applications. So what ST is providing, there are the different steps, the data capture, the build the neural network, so we're providing some tools to help and to facilitate these activities. So you have some hardware, but also some apps on your smartphone to configure the hardware and to offer something that is of use for these data collections. After that, you will have to use the Cube AI neural network converter. This is what we'll do together. And finally, you will have your application running on STM32 with your artificial intelligence. So here, this is one example of the sensor tile. So I think you are familiar with this very small integrated hardware. We'll make a demo of this with Guillaume. So this is one example of the ready-to-use hardware from ST that could be one bricks for this AI applications. Another one is IoT node. So this is the board you have in front of you. So this board is also very nice hardware, ready to use. We have chosen this one because it has a ST-Link integrated. So it means it will be easier to flash and to make some debug on this board. This board has a lot of sensor, a lot of connectivities as well. So what else? In terms of collecting data, so we offer the whole solutions, starting from the hardware, to collect all the data, to offer you some apps on your mobile phone to configure the data. And finally, we are working on developing a huge partner ecosystem solution around the AI. Why? Because this AI is moving applications. Every month we are seeing some new players and we have to follow. So this is really a strategic activity today in ST to follow the trend and to put some innovations with the STM32. So today, when a customer is coming and say, okay, I'm making an industrial sensor, conditional monitoring, and I need to put more intelligence on it. Okay, so what we do is we recommend some partners to help how to build a neural network. And until they have done these steps, ST could support them for the conversions of the neural network into the STM32. So there are different steps, and we have to work with partners because we will not support the whole part for AI. This is too much. Okay, so here this is some example of neural network, so very well-known name like Keras. So this is one we will use today, but there are also Lasagne, Café, and much more. There are many different neural network models that are existing on the market today, and it's growing and growing. Here in the middle, this is a Cube.AI, so this is a converter ST is offering and ST supporting for these activities. And after that, for sure, we target STM32, so the STM32 Cortex-M, but also the MP1 will come in the future as well. So in terms of roadmap, so today we support some neural network from the market, the floating point support. We offer different hardware for the data collections. We will put more features like the tensor flow light support, some new feature with the quantizations, for example. Next year will come the Onyx support and some other feature. So you see we have a complete roadmap in terms of tools and software implementations. What is coming next? Artificial intelligence at the sensor level, at the edge level, is very nice, but more and more you need some accelerator, hardware accelerator. So this is what we are considering for STM32 roadmap to integrate some hardware accelerator for AI. So it will come on the STM32, but it will come as well on the STM32 MP1, MPX roadmap to have some hardware accelerator to support a complete variety of AI applications from the sensor up to more advanced image recognitions applications and so on. So ST want to be present on this market, and we have a complete roadmap in terms of tools and also in terms of hardware. So today we will demonstrate what we have on top of hardware plus the Cube.AI converter. We have as well what we call some function pack. So function pack is complete solutions to make some demonstrations. And we have one ready for the audio classification. So we will demonstrate this, but you will be able to, in one click, to demonstrate different environment you are with the STM32. So this is one function pack. And the second one is human activity recognitions. So this is a complete solutions that we have today available. So we'll make some demos. So to summarize, what ST is offering today for AI supporting. First of all, the Cube.AI. So these are the tools we will show you today and we will practice together. Some hardware reference board, like the sensor tile or the IoT nodes you have in front of you. Mobile application to help you to configure this board. Function pack, this is completely application, the full demo level. The community and the ST partners that we are working to reference more and more people working on artificial intelligence. Okay, the goal is to build a complete community around the STM32 for AI. So here is a summary of the different STM32 families that you are very well aware of it. The dark blue is to show all the families that are already supported by the STM32Cube.AI tools. So this is the majority of the families. The family where you see light blue is is Cortex M0 family. So this is not the the first target for AI applications because you need generally some power processing, but this is supported by partners. And maybe if it makes sense, we will support it in the future as well. Okay, so it was quick introductions to position the Cube.AI, and now I will let Guillaume to go a little bit more in depth in terms of technical.
So today we're going to talk about a function pack for AI called FP.AI Sensing 1. So there are several function packs available here at ST to get you started building application. It could be like an IoT cloud function pack, one for predictive maintenance, or for LoRa. But we'll be focusing on today's function pack called FP.AI Sensing 1. This function pack has two example neural network implementation in it. The first one will be the acoustic scene classification, where it will listen to ambient noise and tell you if that noise is an indoor noise, outdoor noise, or in-vehicle noise. The second one is the human activity recognition. So it will look at accelerometer data and tell you which type of activity you're doing, whether you're running, walking, or jogging, and so on. So it's supported on several of our boards. So you can use the Nucleo platform with the shields for the sensors. You can use the sensor tile or the newly announced sensor tile.box, or the IoT board that we'll be using today. So a sensor tile is good for form factor implementation with battery-powered devices, and the IoT board is great for single board development with the embedded ST-Link programmer and the UART connection. The sensors, they're all tied. The ST sensor are all tied to the hardware using ST libraries and third-party libraries. We have a dedicated ST AI library for neural networks, audio pre-processing, and then on top of that sits the user application to tie everything together. Other features implemented in this function pack are the BLE connectivity. This is just to configure your hardware to send the output communication to the screen and view the results of the neural network. We have a low power implementation using FreeRTOS and the STM32 advanced stop modes. We have a photo feature for firmware update and neural network updates. And then the form factor implementation shown here. So we have the neural network will be running on the STM32L4 microcontroller, connected either to the microphone for the audio input or the accelerometer for the human activity recognition. For the human activity recognition, so this was done using an internally collected data set that we collected using a sensor tile stored on the SD card. We then used that data and trained a model, a neural network model on a powerful computer, and then used the tools like Cube.AI to map it to an STM32 microcontroller. There's also some embedded pre-processing running to remove, for example, the gravity of the sensors. Then the other demo is the audio scene classification. So we also recorded some data internally, and then it can listen to the audio and tell you whether you're indoor, outdoor, or in vehicle. The pre-processing that we'll be using for this is the log-mail spectrogram. So this is just an FFT followed by the mail filter bank application to so that the signal looks more similar to what your ear can hear. If you were doing keyword spotting or trigger word detection, you would be using something like MFCC. Other demos we have is the handwriting character recognition. So this one is shown outside, where you can just write with your finger on this LCD touchscreen letters or uppercase letters or digits from 0 to 9. And this one is has a very small footprint of only 26 kilobyte of RAM, for example. But then we can see more resource-hungry application, such as the food recognition. So this is a computer vision AI application. There's a camera that's able to look at a dish and tell and recognize up to 18 different classes of food. The difference with this one is that it has been implemented in fixed point numbers. So instead of using 32-bit float numbers like we were using before, it will be using 8-bit integer numbers for the calculation. So this will reduce your memory footprint by 4. And it's also faster for your inference time. So now let's go ahead and get started with the hands-on. So we'll take the IoT board that you have in front of you and connect the USB connector to the ST-Link programmer. So then you'll want to open up STM32Cube programmer and go ahead and connect your board, open file, and browse to the directory that's here. C ST Euro 2019 hands-on, workshop 5 STM32L4 Cube.AI. Then you want to look for the function pack sensing 1 version 2.2. This is the same one that you can download on st.com, and look for the binaries for your board. So the reason why we have so many binaries is that there's one for each neural network implementation. So there's one flavor for the acoustic scene classification and 3 different flavors for the HAR. They're being trained, it's either a different topology or a different data set for the training. The ones with BL means that they will include a bootloader on top of the user application. The ones without BL need to be programmed at a specific memory region, and you need to have programmed the bootloader prior to programming the application. So without BL, you will use it for the FOTA, and the ones with BL can be used just out of the box using Cube Programmer. So we'll be using the AST_BL.bin, open, program, download, file download complete, and you can disconnect Cube Programmer. Once your board is programmed, we'll open a serial terminal application such as TerraTerm, new connection, ST-Link virtual COM port, and you want to change the baud rate to 115/200. Once your UART terminal is connected, you can go ahead and press the black reset button, and you should be able to see the startup log of the application. In the log, you should look up for your Bluetooth device address. This will be used to identify which one is your device when we'll go ahead and connect to it using the smartphone. Once your board is programmed, you can use the STBLE sensor app on your Android phone and find your device and go to the audio classification page. So other features of the app are just raw sensor data. You can plot it. You can see your battery level if it's a battery-powered device. But the 2 important tabs for the AI pack is AI algorithm page, where it's either audio classification or activity recognition, depending on which binary you've programmed. And the AI data log page, where you can select which sensor you want to log and enter some labels, and then store it either on an SD card or the external QSPI flash memory. This is very useful to create new models, new data sets, and retrain your model. So now I'm going to show you how the basic concept of the basic flow of creating a neural network. So we'll be using the tool called Keras in Python. We won't be capturing any data today. We'll just be downloading data from the internet and then feed it through a neural network classifier for the training. And then Bartosz will then show you how to convert this to STM32 code. So we'll get the data, do some preparing, some framing on it, pre-process the data to prepare some features that will then be fed to the neural network training, and then we'll build a convolutional neural network classifier, train it using the data that we've prepared, and evaluate it against data that we've set aside. So we have a data set that will be split into 3 different subsets, where the first part is going to be used only for the training to improve the model, and then we have test data set that's it's like new information that's unknown to the model during training, and it's used to evaluate how it behaves. It's just like when you're at school, you're given new questions at an exam that you haven't seen before. So the full pipeline for audio scene classification is you have your input signal in the time domain that's converted to frequency domain and then further to the MEL domain using the log-MEL preprocessing. This is called the feature extraction. Those features are then scaled and fed to the convolutional neural network, where we get an output confidence of each class. This is called the softmax layer, typically found in classifiers. The data set we'll be using, so we're not going to be doing it live. I'm just going to reference the code for you, and I highly encourage you to go and look at the code and try it yourself. The data set is very large. It can take up to tens of gigabytes on your hard drive, so you need a good machine. It was originally found in the TUT Acoustic Scene 2016 dataset. This was a competition, and attendees were given a task of classifying the sounds. It had 15 different classes, so for our example, we narrowed it down to only 3 classes. So like the classes such as bus, car, and train were all merged into one class called in-vehicle. The signal was downsampled from 44 kilohertz to 16 kilohertz. This is the sampling frequency that we'll be using with our microphones, and from stereo to mono. The Python code to download the dataset is just load data into the development dataset with the inputs and ground truth or expected output for development and evaluation. Then we want to frame this input signal. So originally they came at 30-second long input recording, and we want to cut them down to 1 second long clips, so we get even more data. We have for example, 1,170 sample for one case. For the feature extraction, we're taking this 1 second long signal that we're further cutting down into overlapping frames, apply the hand window on it, FFT, melted filter bank application, and then we create each column that we lay side by side. Then we finally apply some log scaling to it to get our 30 by 32 representation of the input sound. The MEL filter bank is just, we take the energy in each filter, sum them up, and apply a log scaling to it at the end. Here's the code to work on all the input features. So we just have, what's important here is the function called feature extraction. It's going to call a submodule. And the other code around it is just to get the correct number of files and so on. Next, we want to prepare the output data, so what we call ground truth, to convert it to the one-hot encoding expected by Keras. So this is each output will be equal to the expected output of the neural network, so the confidence level of each class. So here, for example, in an ideal world, we would expect to have a confidence level of 100% for outdoor. Here, 100% for in-vehicle, matching the input feature number 3. Before we feed our what we call the spectrograms, the input features, to the neural network, we want to standardize them, to normalize them, using the standard scaler from sklearn. So this will have a 0 mean and a unit variance of 1. So all the values will be in between -1 and 1 if we're going into the neural network. The dataset split, as I mentioned earlier, we want to split our dataset between training sample, validation sample, and test samples. The training and validation sample will be used during the training. We'll use the training dataset to feed the neural network. So this is just like the exercise that you're doing during a class. So the lesson, validation sample is, let's say, the exercise that you're doing in the class, and the test is the final exam. So simple analogy. For the neural network that we'll be building, it has 2 convolutional layers and 2 dense layers or fully connected. You can see that the input shape matches the dimension of our input features, a 30 by 32 matrix. And the output shape, the dimension of 3, matches the number of classes that we want to classify. We have intermediate activation functions ReLU. This is to transform the inputs into outputs for each neuron. So from the values, whatever it has been calculated, to from 0 to 1. And then the softmax activation function is to pull the winner apart without really destroying the information of the other confidence levels. During the training happens in different steps. So initially, the coefficients, the weights of the neural network are initialized to random values, and we'll have a very poor accuracy. So then we say, oh, it wasn't trained properly, so it's going to adjust those coefficients to become better and better and learn. This is where you do the learning on a powerful computer like a GPU or in the cloud, and you're creating your model. And it can last from, let's say, 30 minutes to several days, and so on. And at the end here, for example, we've reached an accuracy of 99% against the validation data set. Then if we give it the test data set, so this is unknown data it hasn't seen before, we'd get an accuracy of 89%. Another way of looking at how well our model is behaving is to look at something what we call the confusion matrix, where we can see the accuracy per class. So what we can see here is that the indoor and outdoor classes are not as well recognized as the in-vehicle class. But we still have a actually very high accuracy here. Finally, all of this is done usually by your data scientist and then given to your firmware developer. So the data scientist should provide you with a model.h5 and some test data. The model.h5 is like exporting the model, the pre-trained model, to a universal standard file, which contains the model topology, the number of layers, number of the filters and kernel size, and the weights and the biases. So this is the file that will be used in X-Cube.AI to map it to your microcontroller. Then we can export the data set, so the test data set, for example, into simple CSV file for further validation on the target. So here's a link to the Python code that you can go online and run this code yourself. So next I'll give the microphone to Bartos, who's going to show you how to map this .h5 model onto STM32 code.
Okay, so in order to do that, please start CubeMX. So all of us, we have IoT boards in front of us. L475 MCU is on the top. That's why I propose to start from the new project from Access to Board Selector here, just in the middle of the screen. So please click it. Okay, and you can see the board selector window. And within part number search bar, you can just enter IoT text. And there is very simple selection. The only one board is visible. So just double click on part number BL47. And let's initialize all peripherals with default mode just to speed up the workshop. We are really limited in time. Okay. This is the MCU view. And the second goal of the initialization is to show you how much external peripherals, how much external components is on that board. We have a Wi-Fi module, we have a Bluetooth, lot of sensors, including proximity sensor, external QSPI memory, etc. Okay, so this is CubeMX. we need additional software, because AI in fact is extension of the CubeMX. So here is a hidden option. I agree with you, it's not so well visible. So please click it. And we can see a lot of external components. To make the screen more clean, I suggest to check this option, Artificial Intelligence. And now we can see only 2 items. Okay, so I will unroll, and we have, considering that we have one software package, we have 2 items, core and application. And if you are already experienced with some protocol stacks like Bluetooth, LoRa, Sigfox, whatever, you know that we have protocol stack, and protocol stack, it is equivalent of core in our case, because core in this case it is AI library, it is an object, so closed library, key message for you, for your customers, and the debug capability of this library is of another key message for you. So we have protocol stack, I mean core, AI library, and we need application on the top. As for Bluetooth, exactly the same configuration. So let's check the core to let CubeMX generate the AI library and select the application. And CubeMX is proposing 3 different applications: system performance, validation, and application template. So system performance, it is a simple application to show you the performance, I mean the execution time for the neural network runtime. In neural network wording terminology, we can say the time of inference. So we can skip this application because there is no connection, there is no feedback to PC, any feedback. There is a validation application, so we will use this application and we will be able to validate the real network running on real silicon. I will explain later on what does it mean, validation. And so let's select this validation. Application template, this is just empty application consisting of AI library only and some API interface. It is the case of your customers. But now we are really squeezed in time, so we cannot do it from scratch. Within the resources inspector here, you can see additional software item, the next item. And when I click, I can see X-Cube.AI. So please click on it. And we need to again check both components, core and application. And please don't ask me why. We need to proceed such a way, but I hope, I'm sure that in next version it will be fixed, so don't worry. And we will be we need also the output window to see the debug output. So window outputs, and let's increase. Okay, so the user interface is already configured, and what's next? How do you think? We will be migrating the neural network model to C code. Okay, so let's add network. But before, let's define the model kind. As Guillaume has mentioned just before a few minutes, the kind of industry standard, it is a TensorFlow and Keras high-level library on the top. So we will select Keras. This is another key message for you, for your customers. And we have ready model because we will simulate the updating, the tuning of the customer network, customer model. And in our case, the customer project, customer model will be taken from function pack, because in fact, function pack is marketing name. Function pack, it is just a set of examples of applications. Okay, so saved model, and then we need to navigate to the model. We can do it in two ways. First one is, I would say, classic one, just by clicking browse and navigating to the particular file. And the second one is to by using Windows Explorer and by dragging and drop the file here in this area. So I will show you the second one as a modern one. Step by step. Don't worry, this is, but be careful, this is quite tricky part. So there is a root folder on the paper. So please go to this folder. And within this folder you can find STM32Cube function pack sensing1 v.2.2.0. Root folder on the paper, and then STM32Cube function pack sensing1 v.2.2.0. Okay, let's enter this repository. Again, STM32Cube function pack sensing1, then enter middlewares, STM32AI library, ASC audio scene classification, models indeed, and session Keras mod. This is the audio scene classification model. Very simple network, tens of neurons, and we can drag and drop it. Okay, what's next? We have model, and we would like to, it is already trained. It is already trained. Another key message for you, very important. The Cube.AI, sorry, it is a converter. It converts the pre-trained, and the keyword is pre-trained model to C code. So it means that the model is somehow frozen. It cannot learn more, at least today for the current offer. Buy some workstation, GPU, strong computation power machine. Okay, so we have model based on Python, and then we are migrating it to C code. So the very important step is to check if it fits within our microcontroller. So we need to analyze indeed. Let's analyze. Okay, so we got one strange number and two well-known numbers. The strange number is here, complexity. MACC means multiply and accumulate complexity. It is a number of multiply and accumulate operations to perform the execution, to perform the inference of the model. Why multiply and accumulate? Because behind the neuronal network there is a neuron, and the mathematical neuron model, it is a lot of multiplications. So we are multiplying the input value and weight of the input, and then we are sum it up. That's why multiply and accumulate. And the next two numbers are well known. So the flash occupation is 30 kilobytes, and the RAM is about 18 kilobytes. It is very small model, as I mentioned, just for a workshop purpose. But in real life, for sure, you will meet the big models for image recognition, some computer vision, etc. And customer can complain of the price of microcontroller, or can complain of external flash, but there is a solution. But before, let's validate this model. Okay, so there is a error level 0.01, and we are far from this border. We got some quite nice numbers, So everything is okay. But next key message for you. This is keyword, relative error. What does it mean that error is relative? It means that we are comparing the results for the ideal model, for the original model running in Python on PC, to simulated model in C, also on our PC. So this is relative error. The base is the original model, the Python running model, and we are doing this validation, this comparison using random numbers, random input values. This is due to our limited time. Of course, it is okay, but a little bit, I would say, better method is to use custom data. We cannot do it now, but in real life, we always have custom data because the key point, the key step for the development of neural network is data set, and this is the value in money. This is the value in money, because the structure of the neural network, the number of neurons, it is also important, but believe me, to gather data set, this, as Guillaume mentioned, for this audio string classification for very simple network, the input data set, it is 20 gigabytes of raw wave files. So to gather it, it's a really big job and very expensive. Okay, let's keep that random numbers. So we are okay, but let's assume that the model is really big and we want to provide to customer solution of the price problem. We can compress the model. Let's select compression by 4 and analyze again if we are still, if we can fit within the resources. So the complexity didn't change. It's, I think it is expected because we are playing with the same model, but the flash occupation dramatically drops, but almost by 50%. So that's the solution for you. Of course, not always it is almost 50%, but kind of solution. But this model is somehow squeezed. So let's validate it again on the desktop. If we are still within the error range or below the error range, we are okay. The numbers are a little bit much worse, but it is still okay. So we can stop and play with the network now. And this is network, it is the equivalent of protocol stack. This is our core, so we need to configure application. Let's go to the platform settings. The application is very simple. The debug output is user. So let's select user. And the number of the user is it is user1. Okay, that's all regarding the network and application of the network. Let's verify the clock configuration. The clock frequency is maximum for this micro. It's 80 megahertz. You can lower it, up to you, but I would keep it. And then project manager to configure to enter project name. Please follow my name, validate _NN, and skip this number because for me it is number of the session to separate the. So validate _NN. Then select the target folder. I need to keep my folder, but on your side, please click browse and select any folder. Okay, and let's keep EW ARM v8 because you had it already because of security workshop, L5 security workshop. So we'll use IR. And the last step is to extend the heap size by 0. So to change the value of the heap size from 200 up to 2000. But this is particular setting. It is related to this particular application only. So don't worry, it is not related to the Cube.AI library. Because we have set of buffers in RAM. So and please be careful to not mix the heap with stack. So 2000 on the SFR's value. That's all. Let's generate code. and open project. Okay, so the project is open, and within Project Explorer, let's start from the application folder and user subfolder, double click on main.c. I will show you how the application is simple, because this is just one line. Let's go to the main loop, the line number 132. So this is one function call, that's all. MXX_Cube.AI process. Library is located under lib folder, and as I said, this is an object without debug capability. What about API to the lib? It is hidden behind the middlewares. So let's unroll it. Then middlewares ST. Let's start in the meantime, just to save a time, the building. F7. Please press F7. Okay, so middlewares ST AI. Okay, and we have two subfolders, data and source. And we start the explanation from the data subfolder. There is only one file, network data. I will open it. And you can see an array consisting of a lot of numbers. Yes, coefficients, but in neural network wording, weights. And this is very important part of the application, because we can call it as a meta program. Why? Because most of the functionality is hidden behind those numbers, those weights. This is our program from the learning process, from the Keras. And yes, and the model file, this is I didn't mention it, the extension of the model file, it is .h5. This is hierarchical data format. This is generic format developed by NASA, according to my knowledge, to store the data from the satellites, the map data, a lot of hierarchical data. And so this is not related to the neural network itself. Okay, so this is so the first real value, it is data set, and the second real value, it is here, the weights, the coefficients. And we can migrate, of course not on this level, but on the Python level, we can migrate already learned layers between models. So for example, model A consists of n layers, and m of layers are exactly the same like in the second model. So we can migrate, I can show you, we can migrate particular layers already learned to the destination model. I can show you such a script after the workshop if you are interested. It's very simple, just several lines, that's all. Okay, API, Application Programming Interface, to the AI library. So the second subfolder of middlewares, source, network.c. And let's open the header file. So line number 23, right click and open network.h. Okay, and here is the very nice definition. We can see input tensor and output tensor. I know sounds strange, the tensor, but behind this, the explanation is very simple. It is multi-dimensional array, that's all. And for the input tensor, we have those two numbers, 30 and 32. In fact, our convolutional network is recognizing the pictures. We have picture, and this is the resolution of the picture. And because we are recognizing pictures, we are transforming from the time domain to the frequency domain. There is some issue, maybe not issue, feature behind. We need to gather data. So the conclusion is that we have time quantum. We need to so every second in this particular case, because of pre-processing, because of collecting of the data, every second we can perform the inference of the network. Okay, so this is input tensor consisting of the resolution of our picture, and this is output tensor, and here is free. We have three classes: indoor, outdoor, and in vehicle. Okay, so input and output data structure. And what about the network? We need three steps. We need to allocate the resources for the network model, so to allocate the RAM. So we need to create the network. Then we need to init the weights, so and all the layers. So we need to init the network, and the third step is run the network. That's all. Okay, and those functions you can find below. So network create, and then complementary function network destroy, then network init, and network run. That's all. Very simple. So two data structures, input and output, and three functions. Let's flash the board. Project, download active application. Okay, and start terminal. The communication parameters are exactly the same like during first lab, so 115 kilobits per second. I will start from the font setting to make the visible screen. Then new connection. I'm selecting the ST-Link related virtual COM port and set up serial 115 8-bit character without parity 1 stop bit. And I'm pressing reset. And what is the conclusion? Yes. It's very simple. We need to close the terminal. to free the COM port and let CubeMX perform the action. So let's come back to the CubeMX, because now we will validate our network on the real silicon using USART communication and virtual COM port. Let's come back to the CubeMX and pinout and configuration tab, and then network tab within the network stuff. Now we can validate on target. So we are comparing the Python model as a base with real model working on the real silicon. So let's configure the COM port again. So COM port 8 in my case. Okay, and process just started. It takes a little bit more time because we have additional communication. It is 115. In next release, I think it will be possible to increase the speed. Okay, so the time is a little bit longer, but we got more data. And now coming back to the convolutional layers. You can see here the time of execution layer-wise. So 33, almost 33 milliseconds for convolutional layer 1, 42 for convolutional layer number 2, and all the rest of the layers are not so the numbers are not so significant. I would say we can skip those numbers. The significant impact is on the convolutional layers, because in fact, as I said, it is kind of reduction of the data amount, or we can consider those layers as filters, digital filters. And with digital filters, we have a lot of computations. That's why we got such a timing. And what about error? We are still okay. The number is worse, but we are still okay. So we can use this compressed model, and we can offer customer cheaper microcontroller. That's the goal, in fact, of all this action. Okay, so this is the end of this lab. We have 15 minutes. So I will show you because this application from a practical point of view is useless. We just validated the model, so this is the main goal, and now we need to know how to update the customer project with the new model, which is acceptable. And to do it, I will show you slides. It will be very complicated. You must be very focused. You need to be Windows Explorer experts. That's all. We need to replace 4 files. That's all. Using Windows Explorer or whatever you like. We need to replace network data, so the file which consists of the coefficients, the weights, and we need related header file, and we need to replace the network.c and related network header file. It is API, application programming interface, and then rebuild the project. That's all. You can follow me or not, because copy and paste stuff is as when you are doing it first time can be tricky. So you can follow me or not. I will show you live. We need 2 instances of the Windows Explorer. So on the right side, I'm putting our destination, so the customer project. We'll go to, so in our case, it is STM32Cube function pack. So the set of examples, function pack. So I'm entering the root folder, then middlewares, then ST, then STM32AI library, ASC. Okay, and we have include and source folder. Let's keep this view. On the left side, I will put our source. So the previously just generated project consisting of our new model. So in my case, it is validate NN6. In your case, it is validate NN. On the left side. And here again, validate NN, middlewares, ST, AI. Okay, let's keep this view. And let's start. The structure of the folders is different. It's good from some point of view, and it is problem from another point of view. It's good because it is a simulation of real life. For sure, the folder structures of the customer project will be different than the one generated by CubeMX. So you can practice. Let's start from the include files on the destination side. So it is customer project on the right side, and I'm opening, double-clicking on include. I need to delete the previous job from the previous workshop. Okay, so the good practice, you can follow it or not. The good practice is to mark the old model as an old one, just in case. So you can add underscore old extension or whatever you want, or you can just delete all the stuff. Up to you. And then we need to locate new just generated header files on our source side, so the CubeMX generated project. So within the data, we can see network data.h. I can copy it and paste. And now I need to locate the network.h, and it is located within the include folder on the source side. Copy and paste. That's all. So we already replaced the include files, the header files. Then the last step is to replace the source. So I'm entering my destination, the customer project, deleting the old stuff from the previous workshop. Then I'm marking the old files as old ones. And on left side of the screen, so the CubeMX project, the updated model, I'm looking for the network data.c. So within the data subfolder, I can find network data.c. So I'm copy paste it. And within source, on the CubeMX project, I can find network.c project. Copy and paste to the destination. That's job is done. And now the last technical step is to rebuild the project. So I need to come back to the root folder, and I need to enter the projects BL475, applications, sensing, EWARM, and I need to start IR. Okay, just one button, F7. Okay, so I just build the project, and I cannot download it now from the IR level because, as Guillaume mentioned, we have bootloader, dedicated bootloader, linked to the particular area of the flash memory, and we have application linked to the different area of the memory. And I will use the script to download, to flash the project, and ST-link command line. So the script is located in the same folder as the project file, clean sensing 1, but I'm just clicking.
It's automatically created by the Cube.AI.
And coming back to terminal, we have 3 minutes, so I will show you. File, new connection. And reset. And now I will use command line as a vintage way. I like it. So blue button. And okay, so you can see that it is still functional. Let's wait several seconds, or please just start talking now, because it is silence, and the network model is so simple and not so clever. Oh, okay.